Okay, so I have a dual channel setup right here. Currently, I have a 200 hertz sine wave that's been corrupted with a 60 hertz wave, and the interference signal, 60 hertz interference signal, is being fed into our microcontroller as a reference input, while the corrupted signal is being fed in as the primary input. Over on our oscilloscope, the yellow signal is simply the pass-through from the waveform generator of the ideal 200 hertz signal that we're trying to recreate, and the green signal is the actual output from our adaptive filter. This algorithm right now has been running for a few moments, so it's already converged on an optimal solution and has effectively notched out that 60 hertz interference. If I unplug the filter and reset the filter coefficients back to 0 and plug it back in, you can kind of see the dynamic of how that noisy signal converges on a solution to minimize the error. And this same thing takes place regardless of what frequency I choose to input as my noise. So if I choose 1 kilohertz, you can see that that corrupted noisy signal slowly starts to stabilize back to 200 hertz as those filter coefficients learn how to cancel out that noise. And the filter coefficients are actually convolved with the reference input and fed back into the primary input and summed together to create a type of anti-noise to cancel out what we need to. So the impulse response of the system is iteratively changing with every input sample. And keep in mind here that I've intentionally lowered the step size and I've intentionally lowered the number of taps on the board so that you can visibly see what's going on. Otherwise, the gradient descent algorithm converges far too quickly to be able to see anything in the time domain. But different frequencies converge at different rates. Higher frequencies tend to converge a little bit more quickly, but it also depends on the starting point of our filter coefficients.